All right, so the last thing I want to do with Softmax is derive update rules, just like we did for the logistic function. And in order to do that, I need to take the derivative of the loss function with respect to each of the input variables. So that's what I'm going to do. And if I take the derivative with respect to a particular variable, one thing I can notice is no matter what that variable is, the only term that actually matters is the term that's a 1 in the 1-hat vector. So we just get rid of this sum straight off the bat here and just say, okay, this is going to be, it's actually going to be a 1 at the kth component. And so I'm interested in knowing really the derivative of the kth component of the softmax with respect, or the negative log of the kth component of the softmax with respect to UI. So actually, let me put those right next to each other. So I'm saying I'm doing the following simplification. I'm going from this to this. I'm noting that this is the same thing. So this is a little bit easier to work with. As the first case, let's suppose that I equals k. So I'll look at the derivative with respect to the kth component, which is the one that happens to be hot. Look at the derivative with respect to the kth component of this expression. And so what I'm going to do here is actually the chain rule. So this is actually composed with a negative log function. The derivative of the log, so we'll see natural log here, is actually what we've been working with. Log base 2 makes more sense for information if we're thinking bits, but I'll use the natural log for here. So derivative with respect to the natural log is 1 over whatever is in the natural log. So we'll do that. Okay, so what I have here, like I said, is 1 over the outer, which is the derivative of the log, times the derivative of the inner, so that's the chain rule. And so now the derivative of the inner is actually directly a derivative of the softmax function, which I conveniently have on my clipboard here. So in fact, I guess we're looking at the kth component, so I would say here u to the k over that. And so I'm going to do this with the quotient rule. So I'll say, we remember the quotient rule, which says that if I have a function f of x equals p of x over q of x, then the derivative is p prime x q of x minus q prime x p of x over the quantity of qx squared. So that is the quotient rule for those who don't remember or who are a little bit rusty on that. And so here I'm going to let p of u k, because that's the variable that we're varying here. P of uk is equal to e to the uk, and q of uk is just equal to that denominator there, which actually does involve ek at some point. So we're going to sum up all of these terms here. And so uk is going to be one of them. And so actually the derivatives of these two are the same because the other ones are constant in the denominator here. So I would say that the derivative of both of these is actually just e to the uk, because the derivative of e is itself, right? So I'd say p prime uk is actually equal to q prime uk, which is equal to e to the uk. So now we just got to do a little bit of plug and chug. So let me pause for a second to do that. Okay, so this is what we get when we do, we factor something out and then we group some stuff together differently. And if we look at this, what we realize this over here is actually just the softmax function evaluated at k. And this over here is 1 minus the softmax evaluation at k. So I can write this as, let me just copy and paste that there, softmax evaluation at k, whew, look at this mess, times 1 minus softmax evaluation at k. And so it ends up simplifying to something very nice. Okay, so the derivative of, amazingly, the derivative of the softmax function with respect to the variable k is just the softmax function times 1 minus the softmax function. Well, that that looks a heck of a lot like the derivative we got from the logistic function, and that's really no accident. This is a generalization of the logistic function here. Okay, great. So that's the first case when I is equal to k. Now we've got that derivative locked down. I guess I might as well go, oh, actually, to clean this up even more, because I'm relating this. Okay, that was just the derivative of softmax, which is already kind of nice. But we're doing the binary cross entropy here, and so actually I can plug this in to this. And so what I can say is, okay, what is, let me grab that again. And I'll say, okay, let me plug this in for the derivative. And so I have this expression. And notice that the denominator here cancels out, that we got from the derivative of the log, it cancels out with that softmax in the numerator. So we're actually just left with negative. So here's where it's really nice for the update rule. We're left with just negative quantity 1 minus the logistic function evaluated at k. All right, so you follow through the math and you get this very nice rule for the derivative of the logistic, or the derivative of the binary cross entropy with respect to uk, if k is the one hot. And so what I would say is, okay, for the hot k, the update rule is uk gets actually negative of this. So it would be 1 minus the logistic function of u evaluated at k, or 1 minus the softmax of u evaluated at k. So actually uk gets uk plus the learning rate times that. So we're going against the derivative. That's our rule. So here's our update rule for the hot k. And if you look at it, it makes sense. It says, look, if you're less than 1, you're supposed to be a 1. So I'm telling you, you gotta nudge your u over to the right. Okay, so alpha is a non-negative learning rate, if you remember that. And so if I'm not 1, I gotta nudge you over to the right. Okay? But look how nice that is. Okay, I had this kind of crazy looking thing. You know, this binary cross entropy, which, you know, it comes from information theory, as I said. You work it through, and actually it leads to a very nice update rule for gradient descent when you use the softmax for that. Okay. Now there is another case to consider. That's the case where I does not equal k. So I'll just say in general. We have when I is not equal k, so when I'm not on the hot 1, how am I supposed to update my u in that part of the vector? So I'm going to take the derivative with respect to ui now. All right, now I'm going to speed run through this because it's also going to turn out pretty nice. But so let me just, I'm going to write a few things down and I'll just quickly walk through them. Okay, so once again, I'm going to use the chain rule to bring what's inside of the log to the bottom there as a fraction of 1 over that. And then I have to take the derivative of the inner. Now the derivative of the inner here is with respect to ui, which is not equal to k. So this is going to be slightly different. It's going to start off looking the same. But my p and my q are now functions of ui, not uk. And so when I take the derivative of that, it's going to look a little different. So I'll say p prime of ui in this case is actually 0 because uk does not depend on ui. We're actually holding uk as a constant here. So this is going to simplify quite a bit. So then you know, q prime is going to be the same. Q prime of ui is going to be actually just e to the ui. So I look at this and it's going to be a lot cleaner. So if I plug and chug with my chain rule or my quotient rule again, this thing, let's see what I get. All right, so what we get here is actually quite nice. We have negative e to the ui times e to the uk over the quantity of all of these squared. And what this actually simplifies into is the logistic, or the softmax evaluated at I times the softmax evaluated at k with a negative sign in front. So you look at this and you realize, okay, I take one of the factors in the denominator, pair it with the e to the ui, that's softmax evaluated at I, and I take the other factor in the denominator, pair it with uk, that's the softmax evaluated at k. So this is the derivative of the inner function here with respect to ui when I doesn't equal k. And so let's plug that into the derivative of the binary cross entropy, which is the loss function we actually are trying to look at here. So if I go ahead and plug this thing I just worked on into the partial derivative here, then this is what I get. And I look at this and I say, hey, hallelujah, there's another cancellation, right? So this, the softmax evaluated at k is going to cancel out, and actually the negatives will negate each other. And so I'm just going to be left with the softmax of evaluated at I. That's it. So this whole thing, the derivative of the binary cross entropy with respect to ui of all this actually is just the softmax at I. And so what this tells us for the update rule is that that ui, when I is not equal k, should be updated as ui plus, or I guess I should say minus alpha times the softmax of u evaluated at I. So again, all I did was I took this was the derivative, and I took a little step against the derivative. And so this is also telling me something fairly intuitive. You know, these are supposed to be 0. The things that are not on the hot 1 are supposed to be, I guess I'll call this the cold 0. And, well, the cold 0, it's supposed to be a 0. And so if I look at it and it's not, if this is something greater than 0, then I'm supposed to nudge my u to the left. My u sub I to the left. Oops, I should have said u sub I there. All right, so if I'm on the hot 1 and I'm not at 1, I move to the right. If I'm at a cold 0 and I'm not 0, I move to the left. And so this crazy stuff here, all this, we see works out quite nicely in practice for our update rules. All right? So that's all there is to it. So a nice exercise in the chain rule and the quotient rule together, working quite nicely with these transcendental functions, e to the whatever. Okay, good. So I just am going to have you do a quick little exercise on actually implementing the softmax in Python. And then I'll move on to some more applied stuff.